Okay, guys, welcome. Today we're going to talk about modular arithmetic, or another way of saying this is congruences. Now, the motivation for this is going to come from the fact that we'll use the phrase A gives the same remainder as B when divided by M fairly frequently, so that suggests some kind of special relation. And of course, this relationship is going to behave very similarly to equality. Right? So the idea of this congruence or this modular arithmetic thing is that if A and B give the same remainder when divided by M, where A and B are integers and M is some non-zero positive number, we write that A and then sort of this triple equal sign B, and then in parentheses mod M, right? And then we either say that A is congruent to B modulo M, or A equals B modulo M. And a lot of times I'll just say mod M. We could also say that M is a divisor of B minus A, right, is another way we could say that. Now, notationally, it seems that we want to consider this as something similar to equality, right? We are, in fact, using an equal sign with just one extra little mark there, right? And of course, many of the properties that we have for equality are valid for congruences as long as we're not changing our M, right? So we have reflexivity. Of course, A is congruent to A mod M. We have symmetry. If A is congruent to B mod M, then B is congruent to A mod M. And we have transitivity. If A is congruent to B, B congruent to C, then A is congruent to C. And that's, of course, transitivity. Now, we also have that if A is congruent to B mod M and C is congruent to D mod M, then we're allowed to add congruent things to both sides. We're allowed to subtract congruent things from both sides, and we can multiply congruent things on both sides, right? So we can multiply, subtract, or add. All right. Now, of course, this also works that for any integer k, you can multiply both sides of a congruence by an integer. Okay. One example that you could look at is when m is equal to 2, right? And this will, of course, split the integers into even and odd numbers, right? So these two sets here are sort of equivalence classes, right? Because if you divide any of these numbers, and these are just positive integers, you could also include the negative ones as well, but if you divide any of those numbers by 2, you're always going to get a remainder of 0. So these are all congruent mod 2. Right? So we would usually say, we could say something like 2 is congruent to 4 mod 2. But anytime we have a number here for your mod, we usually would say that this is 0 mod 2. Right? And then the same idea for this one, except these all give remainders of 1. Right? And these are all congruent mod 2. So you'd have 1 congruent to 3 mod 2. And of course, most of the time we would use the smallest number that we could. Okay? And of course, like we said, any two members of that 0 bar equivalence class are equal mod 2, and the same for 1 bar. Now, usually what we do is that for any value of m, we define Zm, right, read Z mod m, where that Z mod m contains all of the positive integers and 0 up to m minus 1, so not including m, right? Right, and the idea is that we stop at m since m is congruent to 0 mod m plus 1 is congruent to 1 mod m, and et cetera, right? Like m plus 2 would then be congruent to 2 mod m, and so on and so forth. All right, that's the idea. Because if we divide by m, then our remainder would be 2. All right, so for example, in Z5, if I take 4 plus 4, that would give me 8 mod 5, right? But that's equal to 3 mod 5, since if I were to take 8 and divide it by 5, I would get a remainder of 3. And then 5 times 2 would be congruent to 10 mod 5, but since that gives a remainder of 0, that's congruent to 0 mod 5. I should say another equals there, right? Now, the last thing that we'll discuss in regards to modular arithmetic is the idea of a multiplicative inverse, right? Now, for the real number system, we define a multiplicative inverse to be some number a star, such that if I multiply a by a star in either order, we get 1 to come back, right? And of course, 1 we consider to be the multiplicative identity. Right, and of course, in most cases, we would say that this multiplicative inverse of any real number is its reciprocal, right, 1 over a, right, with the exception of 0. Now, in modular arithmetic, we don't have this option, right, because we can only use integers. But we do have a multiplicative inverse as well, right, because now we're just looking for something that is congruent to 1 mod n, right? So for example, if you look at Z5, which by the way, let me just write this out in case you're confused. Z5 is 0, 1, 2, 3, and 4. Now, if you look at 3 times 2, which is the same as 2 times 3, that would be congruent to 6 mod 5, right? But since we're looking at mod 5, this would give a remainder of 1. So this is congruent to 1 mod 5. So that tells me that 2 and 3 are multiplicative inverses in Z5, right? Now, if you look at for 4, you get 4 times 4, which would be 16, which would be congruent to 1 mod 5, right? So 4 is its own multiplicative inverse, right? And of course, 1 is also its own multiplicative inverse, goes without saying, because you get 1 mod 5. Right, now what about 0? Zero will not have 1. Right, because you can't multiply 0 by anything and get 1, right? So in that case, 0 will not have 1. Right, so the last example that we're going to do is we want to find the multiplicative inverse of 5 in Z99. Well, we want a number x such that if I multiply 5 by x, I get 1 mod 99, right? So maybe what would be helpful is let's look at the equivalence class of 1. Well, we know that we get 1, and I can also add 99, which would be 100, or I could subtract 99, and I would have it negative 98. I could add 100 again, or 99 again, I get 199, or negative 97, and so on and so forth. Now, what's going to be the easiest number to get to here? Well, of course, it's going to be 100, because we know that if x is equal to 20, which is in Z99, then 5 times 20 would be congruent to 100 mod 99, but that's just equal to 1 mod 99. So the multiplicative inverse of 5 is 20, because 5 times 20 gives me 1 mod 99. All right, so that concludes this video on modular arithmetic. I hope you enjoyed, and I'll see you next time.